sit on Grandpa's lap and just talk with him. Well, one day she jumped off Grandpa's lap and ran over to her mom, and she was all excited. And she said, her mom said, "Why are you so excited?" And she said, "We're going to Disney World. We're going to Disney World." And the mom was like, "Why are we going to Disney World?" And she said, "I was just sitting on Grandpa's lap, and I made him make the sound that a frog makes." And Mom's like, "What?" So she went over to Grandpa, and she said, "What's going on, Grandpa?" And Grandpa said, "I don't know. She just asked me to say, was it ribbit? She just asked me to go make that sound." And the girl said, "Ma, you said when Grandpa croaks, we can go to Disney World." Alright, so terminology can be important. That's how we tie it into the lesson. Terminology can be real. Oh, my mouse is gone. Terminology can be really important. So while we're using electricity and our flow and amp draw, we got to be careful that we're in the right area frame of mind. You will be in your book. I could have typed it on here. Power Plant, Chapter 4. So Chapter 4 of your Power Plant book. It's mostly the first section of the Power Plant book, Chapter 4. Chapter 4 gets into some electrical towards the back, which we already covered. As with almost all your chapters, as you're getting ready for your O's and P's or studying, reading the chapters is a good idea. The trick with this class is the FAA jumps around a little bit. In this class, they're not as bad, so you can kind of follow along where we're going to be. What's hard is we have to jump around and say, okay, we're in page 15, page 1, page 5 during the class. Once the class is done, you should pretty much be able to read through chapter 4 and say, oh, okay, I understand what's going on there. In the same way that your other classes, once you're done with the class, reading through makes sense. We used to try to say read through before class. A lot of college classes do that, right? Read these chapters before you show up to class. And the problem is it often just confuses you more than it helps because there's so many terms that you don't understand. So I recommend reading through the chapters after the class and making sure they make sense. There's a few starting systems, specifically with turbines in chapter 4, that we won't get too deep in covering, so you can skip around those sections. But for the most part, reading through the chapter afterwards is a good way to make sure you're up to speed, you know what you need to know. And if you have any questionable areas, go back and review or come to an instructor and say, why is this saying this? And we can talk to you about it. So that's how I'm going to recommend doing this class. I got to roll through attendance before I forget. Basically, we've got Charlie's gone. Is there anybody else? Does Charlie normally sit by you, Anthony? Do you have an empty seat next to you normally?
Yeah.
Okay. Oh, Mark, yeah. So 1, 2. So I think it's just Charlie. All right. Who are you guys covering for? All right. I am going to pass out a fair amount of paperwork. When I went through here, they recommended we get a big 3-inch thick 3-ring binder. And we stored all of our paperwork in it, and all of our labs, because they used to be in paper copy, went in, and you could go back and review. I've noticed since we went to Moodle, you guys aren't really keeping your stuff. Is anybody like doing a good job? Yeah, there's not a lot. How do you keep yours, Sydney? In a binder? It's not as much to keep, but it's nice to keep it and look back. This class, I don't know, there's 4 or 5 things here. So I think what I'm going to do is I'll hand them to you, David, send it down, send it back, and then that way, and try to keep it in the batch as it goes through to make sure we get everything. So here is the schedule, and on the back side you have your suggested deeper dive and extra learning opportunities, and we're going to go through all these together. Part of the suggested deeper dive and extra learning opportunities is making a buzz box. This was the buzz box I made when I was in class. If you just go buy one already made, already assembled, they're over $100. And they don't have this nice little switch on them. What these do, yeah, they're pretty annoying. That's what the switch is for. So what these do, we're going to teach in depth later, and we're actually going to demo one earlier today. But basically, the black lead is like the common, and when the leads are disconnected, the lights are on, and it's making an annoying sound. That way you don't have to be looking at it. If you build one of these red boxes, even the kits do not come with this switch. So you'll have to drill a hole in the case, find one of these little switches in our little switch box up above Dean's work area, and add to the wiring diagram that goes with it. But there's a little circuit board in here that you have to do some soldering, you gotta put the speaker in, stuff like that. We will sell these to you for $50. We're trying to figure out how do we wanna do this, because basically it's a waste of money. It costs a bunch of money to just supply them to everybody if you guys aren't gonna build them and or you don't use them in the future. If you wanna build it like the voltmeter, it's good practice for soldering, and it's basically just good dexterity, finger practice, and assembling stuff. So we're giving them to you for less money than we pay, if you wanna do it. But you gotta hunt me down, hunt Dean down, we'll get you one. This style, in my opinion, is a little bit better. It looks more standard, it's a little bit more rugged, and it gives you the option to turn the noise off. There's another box that is a plastic box that I have out in the lab. Somebody remind me, well, we'll show you when we go out there. It's a little bit simpler version because it croaks. Instead of having what used to be 30 students, with these going off the whole lab time, we'd go crazy. They go, roar, roar, roar. We call them the little croakers. You might have heard it yesterday. I don't know which one's gonna last 20 years and still work, this one or that one. It's plastic. Anyway, either one is an option. They both work. If you wanna build one, come hunt me down, come hunt Dean down. But we will cover these in more detail later. That is an option. It used to be required. It takes a little while to build those things. Not as bad as the voltmeter, but you know, it's a good, I'd say a good 2 hours to build that thing or more. So if you're like, man, I'm struggling to keep up with labs, I still have labs left from instrument class, you probably don't want to build one. If you're like, man, I was getting bored towards the end of some of your other classes case, maybe you do want to build one. Or maybe you take it home and build it there. We have a whole drawer full of them. You go in the tool room, the bottom drawer of the toolbox is full of those. Most of them are from previous year's students that built them wrong, and then Dean had to go fix them. So we have plenty to use here. When you go work at a shop, they will most likely have one for you to use there. Now that said, Nick took his from when he went through class and he was using it overseas. I used mine once, so it is what it is. Think about that if you want the extra or not. We'll cover the other extras shortly. The syllabus is coming around. Okay. This is front and back, and when we go over your labs, you'll need to fill this out for your magneto that you'll do a 500-hour inspection on. We gotta be careful with our terminology on that, and we'll cover it more later. We don't wanna say rebuild. What ends up happening with magnetos, which we'll cover later, is if you do it according to the manufacturer, especially these slick ones, they will tell you there's a certain list of parts you have to replace inside of it. If you actually buy all the parts that you have to replace inside of it, guess what? It costs more than a new magneto. So there's a little bit of silliness of who in the world is actually going to do it. You guys are gonna go through it so you understand how they work. Maybe in the field, you might want to not rebuild, but you might have to do a repair or replace a component, but even with that, you start getting down to following instructions. We have 10 brand new used ones. 10 from Slick. They'll send us 10 a year if we send them an email that says, please, please, please. That we don't know if they work or not. They send them to Slick for overhaul, and then Slick sends them a new one because, well, it's cheaper to just send them a new one than rebuild it, right? So, some of those work, some of them don't work. As you take these apart, inspect them, fill out that form, we'll hopefully find out if they work, if they don't work. If there's bad components in the one you take apart, we've got boxes and boxes and boxes of Slick magneto parts. So your magneto should work when you put it back together. So when we go over that in a minute, don't get yourself thinking, oh, I got a bad magneto because this part's bad. When you're done with your magneto, if it doesn't function on the test stand, you'll take it back apart and figure out why it's not functioning. Fix it, put it back together until it functions on the test stand, or all your labs won't pass. This one that is, I think, the last thing to go around is a wiring diagram for the shower of sparks, and there's a bunch of different names for that. Shower of sparks, boosted star, Bendix, starting system. We're going to cover that in detail later. I've got random books floating around. Here's like 3 or 4 copies of it. Nice to read through. I recommend reading through it when you get a chance. I think you have it online as well. If you don't find it, come find me. It is a lab we're going to do, and when we walk around out in the lab today, I'll show you how that works. So the wiring diagram is a version of that at the different timings of the engine. We also use this just for looking at our ignition switch to say, hey, what is my ignition switch position in right now? So we touched on this, I think, earlier in the year, but it's coming back up now. So, did everything make it through? I see one. Almost. I'm going to collect those in just a second, and we'll go over the extras. Perfect. Oh, you didn't help them out, huh?
No, I was gonna think about it till halfway.
Okay, well, I'll tell you what. We'll do it later. We'll have Parker and Dan. We'll get them later. Okay. Here is your schedule. I think I have the exam set on the right day on Moodle, if somebody wants to check it. Sometimes I delay those. But it is on, let's see, 19, 20, 21, a Wednesday. Okay, cool. So it's correct on Moodle. The timing's probably off. But so it'll be a final exam, and then we'll review the results the day after to clarify anything you might have got wrong or if there was confusion on the exam. I do have a review for final the day before. This class is one, it's probably the absolute best class, just stretching, for Tell Me Something Barb Doesn't Know. I had so much fun just setting these components out yesterday. I'm like, oh, I just want to tell you guys all about these. Dan's here, Charlie's the one that would need the copy. This day is a great one for grabbing a buddy and saying, what is that? Tell me about it. Because that's basically what you're doing on some of the O's for O's and P's. And this is a great class to just grab a component I have up front and say, what is that thing and what does it do? But we'll do some organized review based on how I feel you guys are doing in the class. When I first started teaching here at SMAT, this was the class most people were failing on their O's and P's. And it was like, let me back that up a minute. I want to drag myself out from under the bus. From a previous instructor that isn't here anymore, that was helping Dean teach it. There was some tag teaming going on. They had the hardest time with timing the magneto to the engine. So, you're gonna notice that I time the magneto to the engine in about 3 or 4 classes, because I'm like, it's not happening in my watch, they're gonna know how to do this. So if you get to the point where you're like, I'm not quite getting that, come get some one-on-one instruction. If you're doing these in a group, make sure you understand what's going on, or go do it on your own. That's part of why, when you look at the back of this sheet that you all have in front of you, it totals 27 and a half hours of, I'm gonna call it estimated case speed. And I realize instrument class, I might have underestimated a little, because there's quite a few of you. How many of you guys still have labs to do yet? Yeah. So I added to my notes for next year, I said, I better add a day to that class, to give them a little more time on labs. This one should be the other way around. It's almost always the other way around. I get nervous on this class that you guys are gonna be not working on aviation stuff and goofing off, and I'm like, if they rush through their labs, I'm gonna have a problem. So 12 and a half hours extra time in here. So, with that, and we're gonna go over what they all are in a minute, you've got your extra learning opportunities sheet here. I wanna go over on your extra learning opportunities sheet, kinda make sure you know what's going on with each one, so that you can do it. Internal timing, we'll talk about later. When we say internal timing, basically we're saying you're adjusting the points on the magneto to time the points when they open in relation to this thing going around. So internal timing on a Bendix magneto, there's basically 3 different Bendix brand magnetos. There's a 200 series, a 1200 series, and then a 20 series. The 20 series is like the same as the 200 minus the contact. So we don't have any labs that say to internally time a S20 Bendix, so it would be just grab one of our S20s and do internal timing on it. Time an additional magneto to an engine. You will have a lab. It says in groups, we'd recommend 2 or less in your group. If you get 3 people in these groups, a lot of times one person doesn't know what they're doing, they're just watching the other 2. I have not decided yet if I'm gonna assign that. Really, we're about 5 days in before you get to that lab. I have your lab groupings from Ryan's class coming up. I was gonna use those, but there's 3 or 4 groups that have 3 people, and I was trying to figure out how to split those up in here. So I'll give that out in a couple days. I might just let you pick your own group when you're timing magnetos to engines in this class. Basically what it is you gotta do a run-up. You've gotta make sure the engine runs and that the magnetos work, right? Because you don't wanna go time your magneto to it and then crank grandpa over and have it not start, and you're like, was it our mags, or is the engine bad? So you start the engine to prove, hey, if I time it right, everything's gonna work. Then you take the mags off, you put your mags on, and then you start it again and go, yep, it works. Sounds silly, but every year, and I hope it's, maybe this year will be the difference. Every year we put a mag on and the thing won't start, we get backfiring, and they timed it 180 degrees off what they should have timed it. And I just bang my head on the wall and say, I covered this ad nauseum. But it happens, because it's fairly easy to do. We'll hopefully show you how not to. So on that one, you will either be timing a slick or a Bendix magneto to your engine for your official lab. I would recommend, if you originally timed a slick, grab a Bendix mag or an engine that has Bendix mags and go time that one to an engine, so that you understand the difference between the 2. We're going to teach you the difference between the 2, but we want you to know the difference between the 2 with your own fingers. Part of that is, you notice it says with a partner. Okay, sounds good. All the way down at the bottom, you have time an additional magneto to an engine all by yourself. And you're like, I thought I already did extra work. Why do you have me doing it again? When you do your O's and P's, if you've got somebody talking in your ear while you're doing it, a makes it either easier or harder. So when you're doing your O's and P's, you'll be all by yourself, so I wanna make sure you're super confident with timing these to an engine by yourself. So that brings it to the third one, time a Surefly magneto to an engine. We don't have any official labs written up this year with Surefly magnetos. Surefly is a brand that's an electronic magneto. We're gonna have a whole class that talks about them, but we don't have any labs tied to them yet. I'm not 100% sure how I wanna make that lab, and for that reason, I said I'm gonna put it in the extra area. There's unlikely you're gonna get any labs on your O's and P's with Sureflies. It's highly likely you'll be working in the field and you'll be dealing with electronic magnetos. So getting a little exposure to them here is gonna help you out in your career, probably more than you're gonna get on O's and P's. But we'll go over that. Adjust the gap on several more spark plugs using various tools for practice. One of your labs is gonna have you servicing spark plugs. And listen really close on this one. You're in groups with your engines for Ryan. One of the first things you're gonna do for his class is take the spark plugs out. Hopefully, you take the spark plugs out and you put them in a nice, handy little tray like this so that you're not kicking them around on the floor. Because in spark plug, class, what we're gonna learn is that's now garbage and it goes straight in the trash. If we weren't at SMAP. We're not flying our aircraft and, we drop them too much. Now, the reason for that we'll learn in class is there's ceramic inside here that could have cracked when I dropped it, and there's really no way of knowing if I cracked it or not. So if you drop a spark plug, it's garbage, you throw it in the trash. Here at SMAT, you throw it back in the box and laugh at somebody when their spark plug doesn't work. But I say that, I did it on the carpet, and I actually have caught it with my toe, because we actually don't want to just go through spark plugs. So be careful, try not to drop your spark plugs. These trays were our sheet metal project when I went through class, because you probably want to have a tray like this working in the field. The shop you're working at will have these. Mine's kind of, well, I don't really like it. If it's fully loaded up, it can tip over. There's double layered ones. But if you need a little sheet metal review, you can take a peek at this one. It's pretty simple. I've got 6 holes. We're gonna actually cover how they're labeled, how you rotate spark plugs, and why these trays help with that later. But that's another, I'm gonna call it extra project. You might be interested in is whipping out one of those. What's interesting is they don't actually whip out that fast. So, for what it's worth, overtime, after hours, or if you're interested in having a tray can help. Otherwise, we should have enough trays around here. But, all that to say, you're gonna pull the spark plugs out of the engines that you're working on for Ryan's class. Those spark plugs are the ones you're allowed to, recommended to, service for this class. Now, if you're working on a 4-cylinder engine, you're gonna be in a group of 2, which means you each get to service 4 spark plugs, because you got a top section and the bottom section. If you're working on a 6-cylinder engine, well, you still get 4 spark plugs each. The issue is some of yours won't be dirty at all, and the group last year hopefully just adjusted them, right? So when we get into spark plug gapping, you're highly unlikely to have to gap the spark plugs out of the engines you have, because they haven't really run any hours since they gapped them last year. But the box of spark plugs that we have out there that's dirty and nasty and they show up from the LLC, those ones are probably dirtier than yours. They probably need to be gapped and cleaned. So I would recommend, highly recommend, and that's why I put it on this sheet, finding a couple super bad spark plugs out of our tray. It's kind of underneath the shelf out where all the engines are stored, and service those ones as well. You will service the ones out of the engine and show them to us, but just for practice, I recommend doing that. We're gonna teach you, it's a whole class on gapping spark plugs, but that's an additional one. Make your own slick and Bendix internal timing tools. That used to be a required lab as well. I had it here, it moved. We changed it, and what you're gonna find out is technically you may or may not need these anyway in timing Bendix. But basically it's a piece of aluminum with a little piece of paper glued down to it. If you wanna do that, I've got a stack of the pieces of paper here. They're somewhere in the Bendix manual if you wanna photocopy. So it would be making this and making this little wire guy. It's just a piece of copper, and it's actually an electrical terminal, which is kind of weird, right? But what happens is that electrical terminal, no Bendix mag, it's out in the shop. The electrical terminal is the exact right size to when we get to that class. Wrong mag, but it basically clips on top of a rotor, and when the rotor goes around, it moves. I'll teach you that in class. So you can make your own timing tools. When we were in class, we actually also made our own, forget what we call that thing. Timing tool, timing wheel, indicator pointer. We used a cottage cheese thing, and you'll see them out there. We're gonna go for a walk shortly and show you where all SMAT's tools are. You don't need to make these. Might be handy for you when you're working on stuff in the field if you're not working at an actual shop. Alright, so those are the extras. What I like to do is I'm gonna do a walk through the shop with you a minute, then we'll take a little break, and then I'm gonna come back and we're gonna dig deeper into the actual schedule, the actual labs, and then we'll get rolling with the PowerPoint. Sound good? Alright, so follow me, and we're gonna show you a few things out in the lab. you steal Ryan's thunder.
And you never know, he might change something.
I thought the groups looked well. I think you're all gonna be just fine.
I know, I see a bar, and I see two little ones on the bottom. And I can see the bottom light.
Yeah.
You guys all, we all will play.
Trevor, yeah, yeah.
All right, welcome back, everybody. I guess I technically should start with the syllabus. For being a bigger class, it's an interesting syllabus. It's not really that long. And you have everything on Moodle. So mostly what I would use that paper for is same as every other class. When you get done with class, I would look through the back for the knowledge, risk, and skills and say, yeah, yep, I'm feeling confident with that stuff. Or, ooh, there's one or two of those I want to do a little bit of review on. Other than that, really Moodle is going to help you out on the syllabus more than anything else. Give that to Charlie when you get a chance. So, we do have a midterm. And the final, like we already talked about. The rest of this is if you get a component where you're like, hey, you didn't teach us about that yet. I'm like, well, it's coming up. So for instance, spark plugs are way out, not next Friday, but the Friday after. So you'll be dealing with some spark plugs potentially before then, but we're gonna do a really deep dive into spark plug and spark plug maintenance on that day. We have, well, it's on the lab for PowerPoint, so I'll wait on that one. So that's your schedule. I gave you, this is the one you have, right? Yeah, is the one. So I would pull this up in front of you a minute, and I'm gonna click my screen back, because the screen you have, the sheet you have doesn't have all these words on there. So if you notice on the one you have, I do have the lesson number that goes with it. So for instance, lesson 11 is spark plugs. If you flip your little sheet over, you'll see that lab 9 is spark plug maintenance. And on your sheet, I have your lab 9 being done way out here. So I went through, I purposely timed the sheet I gave you so that you'll have the class before you have the lab that goes with it. If you try to jump ahead or do stuff out of order, you might not have all the info you need. If you stay with this schedule or something close to it, you should have everything you need. Basically, the labs go in order, basically, with the exception of lab number 8. Lab number 8 is ignition wiring harness. Monday morning, Dean is going to actually have, I guess you'd say the class. He's going to teach you how to repair a ignition harness. He's better at it than me. Every year I say, I'm going to do that next year. I'm like, it's more fun to have Dean do it. So lab 8 is one that you can start right out on Monday. So if you look at your schedule I gave you, there's actually no lab on here for today. My finger's outside. So you can wrap up the labs from yesterday. You could talk to me about getting a timing box, do whatever you want to do today. We're not expecting you to do any labs. Start lab 8 on Monday, finish lab 8 on Tuesday, and start lab 1. You'll notice I have the timing, so lab 8 says it's 2 hours long. So the 2.5 hours. Oh, that gives you the time. So this timing should all work out fairly well in that. So here's what we're gonna do. We're gonna go through kind of the labs one by one, not in super detail, but just so you kind of know what's going on. If you have Moodle up, it might make sense to kind of look at it while I'm going over this with you, but you don't have to. Lab 1 is mainly just Moodle matching questions. So you're going to go to an image that Moodle gives you, and it's going to say, which is the coil, or which is the rotor, and you're going to drag over and match it. I've put right on here as well, some of them are capital letters, some of them are lowercase letters, and every year we get about 3 students that don't realize it, they do half the lab, so now you know. Do the capital for capital, lowercase for lowercase. But that's basically a Moodle lab, so it's fairly short one. Lab 2 is questions on magneto disassembly. It's mostly Moodle. Once we get to 2B, 3B, and 4B, we're going to be dealing with your own personal magnetos. So I thought I was going to put them out today, but I didn't quite get there. Me and Dean will set out the mags on one of the tables, and everybody will get to pick a mag. So you'll notice, kind of like the alternator labs, where there was one lab was disassembly, one was reassembly. 2B is disassembly. 3B is inspection while it's disassembled, and 4B is reassembly and testing. So do them in order, but also don't start working on 3B or 4B before you're done with the other one, because you might not have stuff that you had needed. That goes back to, where is it? The sheet you have. You'll use this for the inspection specifically one. You could start on it on the disassembly, but realistically this sheet is for lab 3B magneto inspection. Should give you everything you need. They might have a digital copy that you could do digitally. It's a wonky shape, and if you print it, it's like 2 or 3 pages long, and it all prints funny. So I printed this one for you if you like paper copy. I recommend paper copy, but you can do that one digitally. It can be a little bit trickier to fill the numbers in on it. We have 6 of these slick magneto kits. We will have a lecture on magneto disassembly and reassembly. There are the lectures coming up next week. I think it's Tuesday, Wednesday, Thursday. There are 27 of you. There are 6 kits. That means, well, you're going to have to share. The problem with sharing is we don't want these kits to go to your workstation. If you need to do the internal timing on it, you can borrow the tool. Go to your workstation with the tool if you want. You can borrow that tool. At one point they were all labeled. So this is kit 1 if you look at the front. Slick number 1. Everything in here should be painted with a 1 on it somewhere. Goes through all the other ones. In order to actually do this maintenance, Slick says you have to have the proper tools. So it's back to, if you're going to work on something on an airplane, you got to follow manufacturer's instructions, and they tell you these are the tools you need to do it. Right down to this little bushing looking guy that has a 1 on it, and I'm holding that up to show you because, man, it's hard to find these at the end of class. Try not to leave this at your desk or put it in the washer file. This is a very specific tool for testing our impulse coupling pawls, and we'll teach you how to do that later, but it's a very specific tool for that with specific dimensions. So we'll go over how to use that kit, but if you need to borrow it for driving stuff in and out, you could bring it to your bench, but we don't want you to. So over the years, Dean has made like 30 of these. They're mostly back in the ignition class box back there, which we'll visit on our next break or lab visit. So what you're gonna do is you're gonna put this in your workstation, and when you're working on your mag sits in there nicely so that it doesn't fall over and it's nice and neat. And if you get to the point where you need to press out one of the components, grab a couple and show you. These two. If you need to press out a component, you can come grab the tools that you need to press out that component, press out the component, and then come return the tools so the next guy can do it. The instructions from Slick, which you do have online, there's like 20 copies in the library, but they keep updating them every year. And it gets kind of annoying to reprint 20 copies of a 20-page book every year. So you have the newest one, I believe, online on Moodle. If you prefer paper copy, well, up to 20 of you can prefer paper copy, and they're in that room. Part of the reason you're going to use the proper tools is this is supposed to have 2 of those ears on there, but our SMAT students did not use the proper tools in here, and they just used a hammer or a socket, and they busted it. So please use the proper tools when pressing stuff in and out. It'll be a whole lab that we lecture on and talk about. The other thing is this is a keeper. It's a magnetic keeper. These are the magnets you're going to learn about that are in magnetos. As soon as you take that out of a magneto, you want to put it inside of a keeper. There's a couple of them in these kits. There should be a whole bunch of them in that 100-hour inspection. That keeps the magnet from getting weak and going bad. There's one portion of your inspection lab or startup lab that talks about checking the voltage. I don't know if we actually have you do that. It's in the Slick thing. If that magnet gets weak, it'll still produce spark, but it might not be hot enough spark. So in order to keep that magnet from going weak, anytime you do it in the real world, put a keeper on it. I'm not 100% sure if we have 27 keepers. So try to put a keeper on it. Ours aren't going on aircraft that are flying. So if we have a keeper, put one on. You will see these laying around SMAT without keepers, but you shouldn't. So that means every box should have one as well, because it's part of the official Slick kit. We could put that as an extra if we could find some iron. All it is an iron ring to allow the flux to go around that. So that's the Slick kit. There's one extra box that I showed you in the room that has a lot of extra screwdrivers and random components that aren't labeled. So if everybody's using these ones, you might find the tool you want in the blue box. So that brings us pretty much all the way down to lab 5, installing the aircraft. I already told you about that. You're going to start an aircraft. You're going to pull the mag off. You're going to put your magneto, I do believe, onto the aircraft, unless we can't find an aircraft running with your magneto. So you might have to look around. If some of the aircraft are using Bendix mags, so that won't work so well. If that's the case, we can just take the magneto off the aircraft, depending on how the lab's written, show it to one of us instructors, say, Dean, I have the magneto off, see? Okay, good. Now go put it back on. So sometimes that's easier, is just uninstall and reinstall the one off the aircraft. Probably the recommended thing. It's kind of fun to see yours run, but see what happens. Shower sparks, I just showed you. I got it all wired up, so at our next break, ask me or ask a buddy to show you how that works when it's wired. And when you walk up to it, there should be no wires on it when you start. That might be written, if you're looking at Moodle, as a 2-person in your groups. I recommend on your own, but technically you could do it with 2 people if you want help. Bendix magnetos, we're going to cover in a lab to know what internally timing means. We will have 2 Bendix magnetos, they're in my office right now, sitting out on a bench, and you're going to adjust the contact points on those. So that's a lab that's separate. Ignition switch testing, you're basically gonna use one of these boxes, go out to an aircraft. If the key is in the off position, and I'm installed correctly, should my lights be on or off? On means our switch is open between them. What our key does is it grounds our magneto out. So what you're gonna do is you're gonna go wire the box to the airplane, and the trick with that is you've got to disconnect the P lead because it grounds stuff out. So you're gonna be disconnecting the P lead from the magneto, I believe is how the lab is written. And then you're going to turn it to both, and you're gonna make sure that the lights come on, and then you're gonna turn it to off, and you're gonna make sure that they both go off, and then you're actually gonna try to turn it past off, because there's a certain AD on some of the ignition switches that if people turn the key past off, it actually ungrounded the mags. So like in an emergency, say you're on the ground and people were like, ah, and I shut the airplane off, and then they go past off and it keeps running. And they're like, oh my word, the airplane's still running. Well, normally we turn the airplane off with the fuel anyway, but it's an AD. So you're gonna hook that up to the ignition switch, and you're gonna test to make sure it works. But you'll follow the lab and it'll make sense. Spark plug maintenance. Turbine igniters, one's a Moodle question. Actually, they're both Moodle questions. And then the last one is you're gonna remove one from any turbine engine. And basically, this guy here, you can, is it the Allison or the PT6? That's easy to get to. Might be the Allison. You can take yours that you uninstalled, bring it over to this box. That'll be out in the lab, hopefully. And you can see if your igniter goes. That's one of those labs. I wouldn't say it's busy work, because it shows you where the igniter's on a turbine engine. There's not a lot that we're gonna inspect on those, so it's more just getting familiar with, oh, okay, that's a turbine. So, that's your list of labs. Seems fairly straightforward, right? Any questions so far? Good. Let's keep rolling then. I think that's about all our boring stuff. Check, check, check. Today's just intro to a bunch. Chapter 4 of your book, if you want the pictures. All right, way back in the day, they had an ignition system that would run off a battery. And basically, if we close the ignition switch, the battery would produce power. It'd go through the primary of a step-up transformer, and it would come through a contact to ground. So, old electrical style, we say, okay, so we powered this coil. What was happening is as the piston went up and down, it would trip a little cam, and that cam would open and close these breaker points. So basically, at just the right point of rotation, it would open that circuit, and the field that's on this coil would collapse on the primary. A collapsing coil on a primary, well, that means we're going to induce a voltage on a secondary, and we're going to get one spark out of it. And it'll go spark. So it's not the vibrating spark you see on our vibrators. It was just one spark from the collapsing field. I don't want to spend the time and do it, but if we took a coil, which is literally what this is, and this is, and these are, if we took a coil and hooked it to our battery, it's that same idea. Remember when I did a wire to it? When I disconnect the wire, the Lenz's law, the inductor part, it says, hey, I still want voltage. It's that same thing, but we do it across a transformer, so we make that little weak spark a very high voltage spark to give us a spark. The problem with this system is, what if I lose my battery? I don't have any spark anymore. So, this is possible, and in an ironic twist, once we go up to computerized systems, we're actually back to a similar version of this. So, this is simpler, it makes more sense. We open the breaker points, we get a spark. Makes sense, but relies on the battery. So, about 100 years ago, we switched over to what we call a magneto-ignition system. A magneto-ignition system is a magneto, which basically, it's got a magnet in it, it's its own generator. So we do not rely on electricity from outside sources. We don't rely on power from a battery to do our spark. This is providing the electricity that we need. So that's what we call a magneto system. They're like 100 years old at least, but they're very, very reliable technology. And if the battery system in our airplane goes down, the airplane stays running. So it's a decent system to have. And then we move over to electronic controlled. FADEC is full authority, but you also just have EEC, electronic control. But we have FADEC, and basically we can get back into the old version running off the battery. So just to kind of familiarize you with, hey, there's a lot of different ways to make a spark. Most of our class is going to be talking about magneto ignition systems. It's the specific way where the electricity is generated inside the magneto.
Yeah, on your previous slide, there was a condenser in that. What does that mean?
We will cover that in a later class. If you notice the condensers in parallel with the breaker points, some people will say it amplifies the spark, and I will kind of cover that later. Other people will say, well, we don't want to have a spark happening here every time it opens up, so instead of having a spark here every time it opens up, the condenser acts as kind of a shock absorber, and it's like, oi, oi, back and forth. So, the real answer, I like that second one, is it saves our contact points, so there's not a spark on the contacts every time. But we'll cover that in much more detail later. Okay, this slide, all I had was explain how a four-stroke engine works. And I'm like, that's Ryan's whole class. I gotta teach his whole class in one sentence. So, we're gonna do a brief version of explain how a four-stroke engine works, because some of you might know this in great detail. Others of you, you know, it might be a new concept. I talked to Christina yesterday. I said, did you teach the auto cycle yet? And if you want to be sound fancy and impress your girlfriend, you or boyfriend, you can say, I learned about the auto cycle today. It was the guy that basically came up with the four-stroke, where a turbine engine is the Brayton cycle, yeah, which cycle's not really a thing with Brayton. It's a misnomer. Anyway, so auto cycle is what we're talking when we have a piston. So the idea is we've got valves that will open and close to the exhaust and inlet, but if I start this at the right point, I'm going to find my spot. Exhaust. Okay, so this valve on this side on this one is my inlet. So the first stroke of the auto cycle, the inlet valve is open, so air from my manifold, which also has fuel in it, is being drawn into my cylinder. So that's the first stroke. We call that the intake stroke. So I'm going to back up in time and say my intake stroke, I'm drawing fuel and air into my cylinder. So that's the first stroke of the auto. Once it gets to the bottom, we go to the second stroke, which is up, and the intake closes. The exhaust is still closed, so now I'm just compressing all that air and gas so that it's a very high pressure. So that's stroke number 2 on the auto system, is the compression stroke. Now, here's where it ties into this class and why you need to know. Somewhere near the top of this stroke, and in a perfect world, it actually happens slightly before the top of the stroke, but for now we'll say somewhere near the top, our spark plug goes off, and it lights that fuel mixture. And it goes bang, and it makes a lot of pressure. All that pressure is what pushes the piston back down. So my valves are still closed, right? Because otherwise the pressure would have somewhere to go. So it goes bang, it pushes the piston back down. And that's where we call our power stroke, because we made a spark, they don't like the word exploded, but I like the word exploded. It burns. You know, exploded sounds like detonation, and we don't like that stuff, but it burns. So we get to the bottom, and once we get to the bottom or somewhere near it, Ryan's gonna teach you in great detail the exact timing and the timing for your engine of when the valves open and close. I'm just using at the bottom. In his class, it'll be how many degrees before or after bottom. But near the bottom, the exhaust valve opens up, and as the piston comes up, it pushes all that burnt gas and air out into the exhaust pipe, and now we're back to the beginning. So stroke 1 is intake, stroke 2 is compression, stroke 3 is bang, power stroke, and stroke 4 is the exhaust. It allows it back out. So if you're unfamiliar with those, make sure you come look at this. This is one of the coolest things SMAT has, because you can actually see that all going on inside. So if I go back to, that's my intake stroke. I drew fuel air mixture in. Basically in this class, we're gonna live in between stroke 2 and 3. So we just got done compressing, and we wanna get ready for spark. And we want that spark to go off at exactly the right time. That time is actually stamped on the nameplate of the engine 98% of the time. So we're gonna learn how to mount our magneto, which inside the magneto, you're gonna get a spark when the contacts open. So we're gonna mount our magneto so those contacts open at exactly the angle of degrees that the manufacturer wants. We call it before top dead center. So we're gonna cover that a little bit more at the end of class, but we're gonna live in between those. Now you notice the piston in between that second and third stroke is all the way up. So if I was gonna jam my little pinky finger in here, I can break my finger at the right spot. I can also, at the end of the exhaust stroke, break my finger again. So I can be correct, I can be incorrect. That's how most people fail their O's and P's, if they fail it, is they're on the wrong time when the piston's all the way up at top dead center. So we want to make sure we're at top dead center of our compression stroke for when the spark goes off. And we'll cover that in more detail later. But that's the Otto cycle, how it works, and we'll cover that a lot more later on. Our magneto has wires going to each spark plug, and in aviation we typically have 2 spark plugs per cylinder. That way if one magneto system fails, the engine still runs. Doesn't run quite as good, and we'll cover that a little bit more later. Ryan will cover that, but it still runs. And we're going to cover the routing of which one goes where a little bit later on. We have systems that use spark plugs and wires coming out to them. We call that a high tension system. A high tension system is going to run anywhere between 12,000 to 24,000 volts on the spark plug. That's a lot of voltage. So that's one reason, if you have a magneto in your hand and you got your hand over the end of it like that, you know, carrying it around, and you're spinning your magneto, be careful I don't do it. Yeah, no impulse coupler, you'll learn about those later. If you've got one with an impulse coupler on it like this, and you're walking around like that, and if you got your hand in the wrong spot, you'll hit yourself with 24,000 volts, which often will cause you to drop the magneto and break it on the floor. We don't want to do that. So, you need to know high tension, 12 to 24,000 volts. That's a lot of volts. The wires have to be very well insulated, and we're going to talk about that later. That's why the wires going to our spark plugs are very well insulated. There are other systems that don't use such crazy high voltage, and they're similar to what's in your car, a low tension system. So in a low tension system, They only have the ignition coil in here. It goes through the distributor, and it goes out to the step-up transformer very close to where your spark plug is. If you worked on a modern car, the coil pack, as they call it, it's just a step-up transformer that literally sits on top of your spark plug. And that way the 24,000 or 12,000 volts or somewhere in between there, there's no wire, it's coming right out of the coil pack into the spark plug. That way the power coming into that doesn't have to be so high, and we can use a little bit more normal wires. And usually that's about 240 volts, if you will. Is that a 100 factor, 240, add 2 zeros, 24,000? Double check. 240. Yeah, that's correct. So, so our ignition coils are a basically 100 to 1 wind ratio in our magnetos. Yes, Leo.
So, we're still talking stepping up voltage, though, right?
Correct.
So why does that make a difference on wiring if voltage is not really?
So your wire insulation is going to be rated at a certain voltage, right?
Not current, or like amps.
The insulation specifically is voltage.
Okay.
The wire size is amperage. We're dealing with tiny amperages. We really don't care what size wire these are, because 24,000 volts, do you think it's going to be high amperage? Minuscule amperage. So the size of the wires almost doesn't matter. But the insulation does matter, because at 24,000 volts, we need really, really good insulation. So, some of these systems were on older airplanes. I like to say, I'm not sure if it's true or not, but I like to say it's because, well, the wire that goes out to the spark plug to hold back 24,000 volts, that's pretty high-tech wire. So some of the older airplanes had these low-tension systems, because then they didn't have to figure out how to maintain super high resistant spark plug wires. So they would have a coil pack. That might actually be one. But they might be more like these, and they're going to have a coil out for each spark plug. So each spark plug gets its own coil pack transformer, as opposed to having the step-up transformer before the distributor. So you're going to want to make sure that if you look at a picture, and we're going to cover the internal components later, but if you look at a picture, you're going to want to make sure you look close at where is the transformer, where I got a small number of windings, big number of windings. Is it outright by the spark plug, or is it before the distributor? Everybody following me on that one? Low tension system has a coil for each spark plug. So let's say we had a 12-cylinder engine. 12-cylinder engine, aviation, how many spark plugs are we going to have? 24. So how many coils are we going to need? 24 coils. That's a lot of coils. That's an exam question and probably a prepware question. They'll say, you got an 18-cylinder radial engine. How many coils do you need? Let's see, 18, 2 spark plugs for each coil. That's 36 coils in a low-tension system. Low tension. All right, moving on. Back to high tension. Our magneto is geared to our engine. It's going to mount on the engine, back on the accessory case. It's going to be geared right to it, so that when it's in the correct position, it sends a spark to the correct cylinder. So we not only have to know when does it send the spark out, but we also have to know when does it send the spark out to cylinder number 1. We always mount our magneto when it's sending the spark to cylinder number 1. So it'll be the spark before top dead center, cylinder number 1. The way to find out when it's on cylinder number 1, on these slick ones, if they're assembled, they're going to have that little pin I showed you. And there's going to be a spot where you can put the pin in. There'll be a L for if it's a left-hand rotation mag. There'll be a R if it's a right-hand rotation mag, and that's if you're looking at the end of the shaft. It's also stamped on the side of there. So If I had a left-hand rotation mag, I'm gonna get it to basically the proper timing to where that pin drops in. We're gonna cover that in more detail, and as you take your mag apart, you'll realize that there's only one spot it drops in the correct amount. Close. The issue is, you'll find out these are geared later on. So I can go around on this one, it's a 4-cylinder, so I can go around 4 whole times until I find the right spot. Come on. Come on. Okay. Just for timing, I'll say you can be slightly off and you can be on the wrong hole if that thing's not perfectly aligned, which is why, no, missed it. Come on. There we go. Dropped all the way in. So now I'm pinned on right. So this should be exactly where my contacts open, which is what?
Right before top dead center.
Well, it's right when it makes spark. So now I need to mount this to my engine right before top dead center. So this is gonna bolt on the back of there. There's 2 ears that bolt on. And how do I know I'm at top dead center? That's how we're gonna use all these tools. But also, it's stamped on the drive shaft, but we're not gonna cheat and use that, at least here at SMEC. Okay. More on that in a later lesson, and I'm gonna pull that out, because what you'd never wanna do is leave those in a mag.
They shoot freeze.
What?
They shoot freeze.
Well, all the gears inside here are plastic. So if you leave that on a mag and then you start turning stuff, you can oval out the plastic gears. All right, here's a picture that shows what I was looking at. Here's the pin installed. See the L here? The R is covered. So if I showed you this picture on an exam, let's say, and I said, I'm getting ready to mount this on an engine, do I have a left or a right-hand turn mag? I've got a right, because I'm in the right hole. The L, I don't have the pin in. I got the pin in the R hole. So it's a right-hand turn mag. I'll leave it off. On a Bendix magneto, there's a little window on the backside, and you're looking at a gear, and one of the teeth of the gear has a little bit of red paint on it, and when that red paint is in the middle of our window, that is where the Bendix mag is timed correctly. There's also, it's hard to see on here, but the gear has just the edge of the gear is shaved off. It's a chamfer tooth. We're gonna cover that in a lot more detail in a later class, but that's how a Bendix mag does it.
So can that be either a right or left since it has both right and left on it, or is it?
The internal components, some things have to be different. So when they manufactured it and you assembled the internal components, that's what determines, is it right or left? But with basically the same components, you could reverse it. It's just as you're assembling the components, how you assemble them will determine if it's gonna be correct for right or left.
And that stamp on the side tells you what it is.
Exactly, yep. Did I have that on the last?
Well, you just mentioned it.
Yeah, it'll be right on this tag. This is slick, yeah, correct. The plastic part is the same, it's the same part number, if you will. So instead of making 2 separate ones, they're like, well, you, Mr. Mechanic, you just have to know, if you're pinning a right-hand mag, put it in the right hole. If you're pinning a left-hand mag, put it in the left hole. All right, so, on our engines, if you are a Lycoming engine, you'll have that ring gear, or whatever they call that on the front of the engine. Flywheel. Yeah, whatever we want to call it. Ring gear or flywheel. Notice where it says TC with that line right there? And it's TC number 1. So, if this little line is lined up with that little dot on the starter, believe it or not, you're at top dead center for cylinder number 1. And that's kind of cool, right? The problem is, when it's on the airplane, a lot of times you can't see that stuff. So, you still have to use our little chrome thing. But, if you can see it, that gives you a good idea. There's a sanity check when you're timing your mag. We're teaching you to use the pointers and the fingers, we'll get to that. But the sanity check is, when you say, hey, I'm at top dead center on number 1, if it's a Lycoming engine, go look and make sure it's lined up. Because if you're exact opposite, that thing is gonna be over on, well, it'll still be here. If you're exact opposite, it'll still be here, but the valves will be in the wrong spot. If you're not even close, it'll be in a different spot. But that's how you can use these to just do a sanity check. Lycoming has this here on the back side of this ring, and we'll cover it in a different class. On the back side of that ring, it has another line that says TC, and you line it up with where the case splits in half on the top. I like to say, there's a little, it's not so much a jingle, but there's a little saying. I say, Lycoming are my top dog engines. What did we do this with so far? We talked about this yet? We might not have. So Lycoming are my top dog engines. I love them because the push rods for the valves are on top of the engine. There's 3 things that are all on top. The push rods for the valves are on top of the engine. When you time a Lycoming, the timing mark on the back of it is lined up with the top of the engine case. And Lycoming, because they're the top dog engines, that number 1 cylinder, it ain't afraid of the prop. It's right up closest to it. So a Lycoming engine has the number 1 cylinder right up by the prop, because it's the top dog engine. So if you remember those 3 things, you'll always know, hey, where do I line up that TC on a Lycoming? Is top of the thing, valves are on top, and number 1 cylinder is closest to the prop. That'll help you with a lot of classes. Continentals, on the other hand, oh, that's still a Lycoming. Oh, I see what I did. Sorry, this is the propeller on a Lycoming, so now we're standing behind the aircraft where the pilot is. So here's the back of this ring, where it says TC1, and what you're looking at is the top of the engine, and here's the seam between the 2 halves. So this is maybe at top center for 1, because, well, let me put it this way. It's at top center for 1, but it might be top center of the compression stroke. It might be top center of our intake stroke, right? Intake exhaust stroke. So it is for sure top center though. So Lycoming is on the top. Continental, on the other hand, this is a Continental engine. Usually it's labeled on the ring that the prop mounts on like that. And notice it says TIC. The I is not a thing. It's still TC. The I is actually the line that you're going to line up with the crack or the seam on the engine. Now on a Continental, is it the top dog engine? No, it's a bottom feeder. The push rods for the valves are on the bottom. You're going to line this line up with the seam on the bottom of the engine, which on an aircraft that's functioning, usually you can't see that because there's a cowl in the way, right? But on some of your engines, or if you're timing it, you'll be able to see that. And guess what? Because it's not the top dog, that number 1 cylinder, it's afraid of the prop. So number 1 cylinder on a Continental is as far away from the prop as it can get. Number 1 is as far away from the prop as it can get on a Continental engine. So if you remember those little tricks and jingles, you'll do well. All right, we are going to take a break, but on your break, or do it another day, you can go look and see if you can find a Continental engine, blue test stand for instance, and on it will be stamped somewhere on the front of it the firing order of what cylinders go first. So Continentals is a pretty common one, 163254. So as you have an ignition harness that's going to connect on here, it should always be marked which one is number 1 on the harness. I don't have a harness in my hand. But as you go around the thing for right or left, the order is going to be, it goes around in a circle. But when you mount it to the engine, you're going to go 1, and then the next one in line is going to go to number 6. So they're not 1, 2, 3, 4 on here, this one is gonna go in a different order. So, if you go look at an engine while you're on break, find that, but otherwise, we'll do this in more detail in another class as well. So, take a break, come back at 10:02.
How they work, get into
Yeah, briefly. We're gonna get into that in different lectures.
You said about the old style, you just use the battery.
Yeah.
This is more magnet.
After break, we're doing how they work.
All right.
How is it that you tell that the valves are in the range?
I'll show you. We haven't quite gone over it, but I'll show you here. On this one, that's a good one. So on this one, it's cut away so we can physically look at it, right?
Right.
So as I'm going around right now, they're both closed, which is probably the power stroke then. So coming back up, that's my exhaust valve. So exhaust, intake, compression, bang. So we're gonna wanna time the mag on that compression stroke just before top dead center. But if I go to top center right there, if we look at this, let's see, push rods on the bottom makes it a continental. There should be a TC. Oh, of course.
No, it'll be right there. It's on this side.
Yeah.
TC with line.
Does it say TC on it?
Yeah.
Oh, yeah. Yep. So if we line that up with the bottom crack, that's where our piston's right at the top. So we're gonna go over in the next class. In order to find that, we're actually going to go before top dead center. We're gonna put a stopper in to say, oh, okay, I hit there. We're gonna go see where it hits the other side.
Through the plug?
Yep, in through the plug hole. Yep. So we'll be able to physically find it as opposed to looking at the flange.
And, sorry, that tells you where top center is, you just go before that. You don't put it on the line to time it?
So it tells you where top center is. The engine will tell you where before top center, and usually it's about 24 degrees.
Okay. Oh, I see, almost.
Yep, and if I spin this around, oh yeah, here's TC. So, this one's all wore out. But you got a 32 and a 20 some. On the ones that aren't wore out, they'll actually have stamped in that range. So theoretically, you don't have to use this.
Right.
You could
Just go right there.
go there. The issue is usually you can't see it good enough, and most manuals have you use that. What people mess up is they will say, hey, I'm top center, right? But that was top center of my exhaust stroke. So the main is, how do I know I'm top center of my compression stroke, is we'll put our thumb over there, and on that one coming up, it should be trying to push my thumb off.
Okay.
On the exhaust stroke one, I'm not pushing the thumb off, but we'll cover that.
Okay, cool. And this is Continental. Lycoming
Yep,
is the.
valves are the bottom, Lycoming, these valve push rods are up on top.
Cool, thank you.
Oh, this is Charlie's.
Going like this way,
And then tomorrow, he says his jaw hurts. What is a broken jaw?
Let's go.
What's hurting? That was a very quick response.
That crap had me laughing so hard, I love
Hey, Micah, is your jaw feeling okay?
What?
Is your jaw feeling
say close to 50 pounds.
I think
My,
your track bag
my
is super
track bag.
fast.
This
I would
thing, I
think
feel
it's
like is
shirt roof.
65 pounds.
And they don't care as long as
They don't
it's
care. They don't care. I had like when I got from like
Yeah.
that's with each other. 8-hour layover.
You'd be mad.
When I was from here, and I had to like
Yeah, this one guy tried to go swimming in his underwear,
I have to stop
and he was
like
like,
sit
dude,
down.
you literally, there are children around. And he's like, let's
my
just
brother's
do
like
this,
just
and then some
through there.
poor dude
They were, like,
swimming in the
talking.
last lane with his Speedo, and
Apparently
that
you got
guy's
free
Speedo,
food.
like,
Free
swimming
food
through.
to go to the
We're like,
over like 3 and a half
gotta
hours.
leave.
And it's not
And
the
man,
type
he
of-
was about to throw hands at one of the lifeguard, I just
So I called my brother.
away,
So they
like,
tried
how do you deal with
to
this?
get this ticket. I'm like, oh no, come go down this way. Like I had them on video and I was looking at
Like
I
one
was
bite,
looking at.
I don't wanna gang up on that.
You guys have no idea where this is.
He was like,
Stop
big
lying.
buff, tall dude, and I was like,
Just find the helmet.
All
Go down there.
No, all airports
Like,
look shit like.
and it
I
just
feel like
kept
airports
getting
are hard to find these
It
way
kept
around.
getting
So
worse
Yeah.
because
I was like,
at first
if
when
this
you're like,
were-
oh,
I'm
your
just
daughter
gonna
can't
stand
swim,
this
well, like,
$6
blank, like they were like having like the close to the water pool, and then we're like, okay, whatever. Lots of men were like, hey, you have to actually be in the water. with
I'm
me.
the one walking
And
here.
At this point, I was also
then he
the
takes
only
off his
person
pants
that-
and he's trying to swim in the underwear, and you're like, you actually have to
Well,
wear pants. And then he pops his pants back on after a big fight and tries to go swim with his pants on. He goes, you have to wear a swimsuit. What's
Yeah, definitely.
See, I think this would be
Okay,
right
right.
for my quarter ride. He tried to follow, because it kind of like, tried that deal where like, they can sit down and like,
Yeah.
and it's also, it's gonna have a little too.
Yeah.
I don't go back and forth, but
Like this one too?
zip it up and.
Yeah,
See how it's
if you're
getting-
a parent bringing kids to the
Yeah.
swimming pool.
Which I
you
did
should
find
wear
me so
But-
angry, but then he was
Yeah,
going
that's what I
off
like
about not
This
being
one
able
was
to
bigger.
wear his underwear, which was to the point where I'm
Like,
like,
once again, that
buddy.
was another selling point for me,
Yeah.
but I find
I
out
will,
use it.
like, you just.
There's a lot of stuff that I'm finding after I bought it.
Well, you wipe, so it's like, you can't just let you get there. You can't like, it's like you're in a. Yeah.
Probably not.
Everything is out.
I was
I have traveled for like a
Yeah, but this is
and it's nice that it's
instead of like, once again, I really want to look at my it's not a great back.
Oh, boy. I hate it when you confuse yourself right before you start teaching. Right hand turn magneto. I'm turning the magneto to the right.
From which direction? Right, is it the way it's looking at it?
It's looking at the shaft. Let me double check that before I teach you backwards. Right hand rotation magneto. Oh, come on. Alright, I'm just looking up an image because I don't want to say it backwards and confuse you first. We say we have right hand turn magnetos and left hand turn. And I'm 99% sure I know the answer. And I'm like, oh, second guessing myself. I don't think that's in, well, it should be in your book. Yeah. We'll just go with what my 99 is and hopefully I don't have to backtrack on it. So, when you're looking at the magneto, if it's a, well, let's look at this one. I'll say, it says L on here, rotation left. So this is a left-hand rotation magneto. Don't confuse that with, it's the left magneto on the engine, right or left. Like, that's not what we're saying, because there's two magnetos, right? It's the rotation. So this one says rotation L, so it's a left rotation magneto. So that's looking at the shaft, that means we're gonna be rotating this to the left, so counterclockwise, if you wanna say. Make sense for everybody? So what's interesting on these, and you'll learn as you tear them apart, there's one gear inside it. Oh, I didn't have one with a gear. that the gear goes between the magneto and the distributor block. Thought I had one set out. Here we are. So this distributor block sits on top of here, and there is one gear that is going to engage on the teeth on the magneto and engage on the teeth on here. If we only have one gear exchange, that means we're going to reverse the rotation once, right? So what happens with magnetos is if I look at it and it says left hand, here we go, this one's a right, yeah, we can confirm, good, I'm correct. That's all I had to do was find one that has an impulse, because if I go the wrong direction, no impulse. If I go the correct direction, the impulse works. So, looking at it, what happens is in that gearing, it reverses the rotation. So, if I've got a left hand magneto, when I spin it around and look at the wires that are going to connect to the back of my magneto, it's still going to be left. So even though I spun my magneto and you'd think it'd reverse, it doesn't reverse because the gear did it for you. So, just so you don't all confuse yourself on right or left, I can't remember, does it reverse or not? The gear reverses it from the shaft to the output. So you're using the same thing. If I look at it, if it's a left, this is turning left, but also the spark is going to travel in that left direction, which I'll show you on the board in a second.
What's the point of some turning left and some turning right?
It's how it's mounted into the gears back here. Does the gear that's driving it happen to turn it left, or does it happen to turn it to the right? Come on. I had it all connected where it was happy. There. I don't have all the gears on here that you will on your engine, but you got a gear case. Your magneto basically is going to plug into the back of here, and one of those gears is going to drive it. So it just happens to be where it's living, how they geared it. It's going to have to go one way or the other, and we didn't decide to engineer them all to go one direction, so it's just how it lives on there. If you go much deeper, we get way off in the weeds, because you're like, most our engines run counterclockwise, but every once in a while, you get one that runs clockwise, and so you just got to know what's stamped on the side of it. All right, so if I go to this image here, and let's say we have we said right turn magneto, that's how I have it pinned, correct? So this image would get this harness, this is a slick harness, and I'll show you the picture of it. On the slick harness, see that number 1?
Yeah.
So that means that this wire is cylinder number 1. Okay? So that wire with the 1 stamped on it is cylinder number 1. Now, the aircraft maintenance manual will hopefully tell you which wire goes to what cylinder. That's kind of one way to do it. But you can just look at it and figure it out. So if this was the engine we have, and this is the mag we have, and this is cylinder number 1, we already decided I got a right-hand mag. It must be printed on the side. I got it pinned in the right. So this one is going to go to cylinder number 1. We said right-hand mag, so if I go clockwise or right, which cylinder is this one going to go to? 6, okay. Then I go to the next one. Which cylinder is this one going to go to? 3. And then this one. Yeah, so everybody get the idea behind that, of how that works. So we're going to cover that in more detail when we get to the actual distributors, but that's what's going on and why when you look at it and reverse it, it's still the same right or left as there's one gear that you'll see later on when you take them apart. Okay, we're going to leave some of that basic stuff, which we'll cover more later. I was talking to Christina and laughing. A day like today where it's kind of an intro overview, you guys have really good questions, and our answer a lot of time is, you don't need to know that right now. I actually had a student that didn't like me last year because he asked a lot of really good questions. He's like, it really helped me to know that right now. And I said, yeah, but I got 28 other other students that I gotta keep going through the lecture. So if you have a question, by all means raise your hand. I'll answer it maybe, but I might say, 3 days from now, we're gonna cover that in more detail. So, moving on to some more of the basics. This image shows single and dual magnetos. This is tricky for me because I'm stupid. And if I'm thinking of an airplane that has dual magnetos, my brain says 2 magnetos on the airplane, right? But that would be incorrect. So, dual magnetos mean I actually have 2 distributors in the same mag. And we're going to show you in a couple images that are a little bit better. So this image has 3 single magnetos and 1 dual magneto. So single magneto, single magneto, single magneto. Whoop! I've got myself a dual magneto. Basically, we're saying the magneto will do both sets of spark plugs. So everybody tracking with me on why we call it that now? It's so confusing to me. You go, hey, my aircraft has a dual magneto. I'm like, that means it's going to have one thing bolted to the engine, and basically we're going to have 2 sets of distributors there. I got to go back a slide because I think I was supposed to share something. A dual magneto has 1 rotating magnet. So if we were to pull this apart and dissect it, what you're going to find is there's going to be a rotating magnet in the middle, but the electrical components are what there's 2 sets of. So on this one, same thing, 1 rotating magnet in the middle, but 2 sets of the electrical components, distributors, gears, stuff like that. Isaac?
So if something goes wrong, you don't got a backup plan?
Kinda, yeah. So the interesting part with that though is the part that's rotating, it's just a magnet. I mean, what could possibly go wrong? As far as the contacts that are opening and closing, the capacitors, the little distributor finger that's going around, you got 2 sets of all the components that I'm going to use would typically go bad. So all the stuff that would typically go bad, you have 2 sets of. So they kind of covered it. Aviation's all about weight, and theoretically that one weighs less. So we'll go with it. But pretty uncommon for the reason you said, and man, those things are expensive. And they're kind of heavy, hanging off the back of the flange. There's some issues there with that too. So you don't see these very often. Okay, we're going to take a brief toe dip into this image and full register neutral, how a magneto works. So, inside a magneto, you've got a rotor that's going around. Most of our slick rotors are actually only 2-pole. I've got a north and I've got a south. Most of the images in your book, they give you a 4-pole rotor. So it might be a 2-pole, it might be a 4-pole. For whatever reason, the FAA wants to draw their pictures with 4-pole rotors. It doesn't make that big of a difference in how it functions. If I was going to draw a 2-pole rotor, I would still draw that piece of iron. Oops. And now I'm just going to put my 2-pole rotor in between the iron like this. Okay? So a 2-pole would still work. You could otherwise take this picture and say, hey, I'm going to put the rotor in the middle with a north-south and make it a 2-pole rotor. So the reason they went to 4 is on a 2-pole rotor with 1 full rotation, I'm basically going to get 2 events. I'm going to get a full register one way and then a full register the other way. With a 4-pole rotor with 1 rotation, I get 4 events, but we're not going to get too far off into the weeds on that until after I explain it. But make sure you know kind of the difference between 2-pole rotors and 4-pole, and realize that most of your magnetos that we're dealing with, the slicks especially, are just 2-pole magnetos. So we're going to have this magnet that's in here that's spinning around. It's driven by the engine. And actually, I'm going to draw it back up, north, south, so that's my rotor. We'll draw the housing. Okay. And just for the fun of it, we'll draw the primary coil as well. All right. So, when it's in the position where the lines of flux that want to go from north to south, right? Whatever hand rule we kind of use, but lines of flux want to go from north to south. When it's in the position that those lines of flux go through our iron of the magneto and cut the coil, that is what we call full register. So I edited the slideshow for this year to give you this slide just to make sure you go, okay, full register, basically I'm getting my full lines of flux is what you want to be thinking. So full register is full lines of flux. Neutral is the opposite of that. Neutral is basically I don't have any lines of flux going through my iron core. On this image, the primary coil would be wrapped around that. So neutral, basically the lines of flux are just going to go from north to south on this 4-pole, or if I redraw this one, north, south, I'm going to have lines of flux that go like that, right? Maybe some go through there, but they're really not. They're not doing anything because whatever's going that way is going to get countered. So in neutral position, I do not have any lines of flux going through the iron core. So everybody with me on neutral and full register. Okay, this next little phrase is going to be why a magneto actually works. When our lines of flux are going through there, that is kind of like on our alternator where it's cutting it, right? And it's going to be cutting it. We could do our hand and do all the coil laws, and I'm not going to mess with them because we're not there, but we're going to say this is going to be where the flux is the strongest this way, and if I turn this so that it's south and north, the flux would be strongest the other direction, right? Same thing with this one. If I turn my north and south, I would say now my lines of flux are strongest the other direction. So, as those lines of flux are building and collapsing a direction, that's where we actually make voltage and where we make the potential to have electricity. I'm going to shift your thinking a little bit. It's really helped me. In full register position, think of it like you've got a swing set and you've got your little son or daughter on the swing and they're way up to the side on one side or the other. So they're over here in full register, they're way up high. They have the highest potential. And if they go to the other side of full register, they're way up high, they have the highest potential. Don't get yourself confused by thinking that's where we want the spark. That's just our highest potential to say, hey, I want to send voltage in one direction. What happens is we're going to actually take the spark at the point where the swing is at the bottom. How many of you have walked in front of a swing before and got clobbered? Where does it hurt the most? At the bottom, right? Because basically we've got the most movement going on the swing when you're at the bottom, and you get hit at the bottom. So if you were to take a snapshot in time, you would think when the swing's at the bottom that, hey, if I get hit when it's down there, no problem. There's no issue. But in reality, because we're dealing with motion and changes, when it's at the bottom, that's when it hurts the most to get kicked by somebody on the swing. When it's up at either side, well, there's a potential to get kicked, but you're not getting kicked. So we're actually going to take our spark off when it's very close to that neutral position. And I say very close, we'll deal with why not exactly. But what we're doing is we're changing from, let's say, a positive direction to a negative direction with our voltage, and we're changing the fastest from positive to negative at that point. So we're converting our magnetic field to an electrical signal. And if we're talking an AC current, what we want to do is we're catching it when it changes from positive to negative. It's actually the highest rate of change in that neutral position. And the rate of change is what the flux field is cutting lines, right? So the highest rate of change is actually in the neutral position. That's why when it's in the neutral, that's when we're going to take our spark off of there. And we're going to get to how we do that in a minute. So if you think of it like a swing set and think full register is up high with my highest potential. I got all kinds of flux going through. Neutral is, well, there's really no flux. The swing's at the bottom. But that's the highest rate of change. When you're on a swing, when are you moving the fastest? At the bottom. So that's the whole idea is neutral is there's the highest change from one direction to the other. That change from direction to the other is where we're at. So this image in your textbook, the reason is when I was a student at one point I had this line figured out, and now I can't figure out what they're trying to tell us anymore. I don't know if they changed or not. But what they might do is they might point at this on a question, and they might say, when are we going to get a spark? And the answer is, we're going to get a spark really close to that neutral position. What we have found is if we do it slightly after the neutral position, because we add in some capacitor effects and stuff like that, it's the best. So notice here is where we're going to be getting our spark on this, and it's just after the neutral position, just barely after those neutral positions. So it's not quite exactly neutral, we do it just barely after neutral for a couple of reasons. So what happens is we have our contacts closed, we're rotating that magnet, the lines of flux are changing, and just after that neutral position, we open the contacts. So at neutral, we have the highest change, which means we induced the highest amp draw. And when we say amp draw, we're literally, with our generator, with the coil, we're literally dumping power from ground through the coil back to ground. We're not actually powering a device. So we're doing that through our coil. And right when the amp draw is the highest, we say, hey, I see you're really high. I'm going to open the contacts. So we open the contacts when the amp draw is the highest, and all of a sudden I go from a really high amp draw to no amp draw. That's a collapsing field, isn't it? Collapsing field. So I went from my highest amp draw to no amp draw as fast as I could by opening the contacts. Well, what's not shown in this picture is that's where our transformer is, out to my spark plug. So when the amp draws the highest, I open the contacts and I get this huge change in flux field that collapses across my secondary coil and just makes a tremendously huge voltage that wants to jump across the air gap in the spark plug. So that's how we actually make spark, is it's not the electricity going through that makes the spark. It's, we had electricity going through, and we open the switch and say, not anymore, sucker. And that sudden stop of amp flow makes that field collapse. The collapsing field collapses across the secondary, making a huge voltage, and we get one spark.
So, okay,
Yep.
you open it just after the neutral,
Just barely, yep.
and you're saying that is the position you have the most amp draw.
Yeah, the neutral we have basically the most amp draw there.
My dumb question, why is it the most amp draw if all the flux is out?
So,
Like, it doesn't look
yeah,
like there's any.
flux
or at least-
is not amps.
Okay.
Flux is a flux field, what causes amps is a changing flux field. So if we move a wire, oh, it's in my mouth. If we move a wire through lines of flux, or another way to say that is if we collapse flux,
Okay.
so we got this flux field with all our flux lines, if that field goes boom, back to nothing, all those lines of flux that built, and then when we open the switch, that magnetic field that we built goes, oh no, the switch is open. I don't have a electricity flow anymore. So this flux field I built up goes boom,
Okay.
really fast. It's that collapsing that causes the amp draw. So it's not, we're transferring 3 times, right? So this flux induces an amp flow in the wire. That amp flow in the wire now creates its own flux field. And then inside this flux field, we basically have our secondary coil. So,
Transformer.
yep. So when this flux field here collapses across that coil, that's when we generate a huge voltage on the secondary.
And it does because in neutral position, the flux is down at the bottom. So that's, you're stopping the flux up, which is collapsing the field, inducing.
Yeah, well, it's a change in flux with our magnet creates our amp draw on the wire. Once we have amp draw on the wire, that is going to want to either build or collapse. So
But in the neutral position though.
in the neutral is where
You're-
our flux is changing in the core the fastest.
Right, but that stops the.
You could
flux
say
field on the
reversing.
primary coil.
Yeah.
Which then collapses and induces it into the transformer.
Yeah, so when are we gonna, another way to phrase it is, if I had a wire, only that wire tests all. When is the amp draw gonna be highest in that wire?
At starting at, or at building and collapsing.
It's gonna be when this flux field is changing the fastest. So it's not when the flux is the highest, because if we just take this magneto, I can position this in full register. I'm not making any amp draw on the coil right now, because it's just sitting there, happy, nothing's happening. It's when I change this flux field from one direction to the other, and this flux field is changing when I induce the amperage here. So when I have the fastest change, if I spin this really, really, really fast and go back and forth, back and forth, back and forth, the faster I change it, the more change I have, the higher voltage I could induce theoretically. So we're changing it from flux to amperage. That amperage then produces its own flux, and then we change that flux from flux to amperage. So we're going from, it's back and forth timing wise. So, and that's back to why we don't want it at the highest flux, we want it at the highest flux change. So that's what you gotta be remembering. So, all that to say, we'll deal with this more, I even have the note, don't go too deep, it's on lesson number 3. All that to say, the spark happens when the point's open. If you remember nothing else, you'll pass your O's and P's for the most part. Spark happens when the point's open. Spark happens when the point's open, and they're gonna open just after neutral. Alright, we got the point across? Yeah, so whether you know why or not, the spark happens as the points are opening, and it's because we interrupt our amp flow. Alright, on this one I was just gonna ask you to draw full register neutral, but we talked about that long enough. This is a little bit better picture that shows kind of the full system. Our coils are kind of wired like this, and we'll deal with it later. Is this in full register or neutral position? Who wants to answer that one for me? Yeah, neutral. Yep, I don't have lines of flux that are happily going from north to south through there. So this is neutral, and if we look, oh yeah, look at that. The contact breaker point is just opening right now. So we are fixing to make a spark, and if I look, I can find the spark there. So our points are opening, which means the field is collapsing from the primary, because the points are going to connect the primary coil to ground. We're going to cover how the coil's actually wired, but the secondary coil goes to our finger through the spark plug essentially to ground, and then back to ground. It would actually technically go through those same points, so every time we had a spark, we would spark across the points. That's not real good on the points, right? So what we did is we installed a capacitor in there so that when we open the points, instead of sparking across them every time, it basically just draws a bunch of electrons from one half of the capacitor to the other half. And I can see your brain, Micah, because mine does the same thing, going, wait, does that even open the points then? And the answer is, yes, your points open, your capacitor, essentially while the spark goes on, it's getting the spark from the one half of the capacitor. It goes one way, and then as we reverse it, it goes back the other way. So we're going essentially back and forth into the capacitor with our spark. Alright, so what happens then is our distributor, which is geared down slower, whoa, and we'll cover this more later, but our distributor is going to get that voltage off of the coil that's inside our magneto. Am I missing one? Right here. So that coil off the secondary comes off this little tab, which on that little tab, it basically runs on this carbon piece on the wheel. And on the other side of that carbon piece on the wheel is a little brass, typically pointer, that's going to run around the inside of the distributor, and it's going to point at whatever wire wants to get sparked. So this thing's going to rotate much slower than what the whole magnet on the magneto is, right? So every time the point's open, he better be pointed at one of the spark plug wires. So what's interesting on a high tension, remember this is high tension because we got primary, secondary with a transformer in here. On a high tension, there's ever so slight a gap between this distributor point and the wire for the spark plug. So guess where else you're getting a spark every time you get a spark? You're getting one in here, but the gap between this and this is tiny. So the spark that jumps across here, we're not really counting as much of anything, but it's there, and we'll talk in later classes about how there's vent holes on here, because if we make a spark, there's a little bit of heat, but we're also making ozone, and we want to get all that corrosive ozone out of our magneto. So that's how our distributor works, is that little finger's going to go around, and we will cover that in later detail later. So all that to say, and my thing says to confuse you, when do we get a spark? It's when the points open. It's when we're getting the spark. Yep, got it, covered it. A few terms. We talked with full register. Full register is when the flux is going through. Neutral is when it's not. Primary, secondary, condenser, capacitor, and Lenz's law was just back to if there is a amperage through a wire, there's going to be the back EMF that wants to fight it. But we're going to talk more about Lenz's law later when we talk about some of our wires. So our distributor, here's a blown up view of what I just showed you. It gets power from this little tab on the coil. It just sits on there and gives it power. And here's a blown up view of the inside of the distributor. The other side of this wheel was what sits on the tab, and that finger is coming around, and it's going to just barely miss those guys for sending power through the wire out to the spark plug. Alright, this is a slight review one that you already saw. On the Bendix mags, which I brought in, they look like these two. A little different brand, and they have a cam that's got switch or contact points that you can look in and see there. We're gonna have to adjust those on the Bendix. They have a window opposite the magnet, so it'd be under that screw, or it would be on this one, opposite the magnet, so under this screw. And that's where you're gonna look in and see the window. So the Bendix have the window, you're gonna line the paint and the tooth up. I recommend looking at these, you know, as class you'll get further. Where our Slick has the pin that you're gonna pin in there. Okay. I don't even know if I wanna ask for more questions. I got about 3 more slides that are off topic, and then we're done. Turbine igniters. You saw me spark them ahead of time, right? We got a whole class that we're gonna cover them later. It's gonna talk about different styles like surface gap, recessed, shunted, but basically on a turbine, do we have to time it correctly? We're just letting her rip, or click, 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 or whatever we do. So a turbine doesn't have to be timed, so all this timing shenanigans goes out the window on a turbine. We just need to light it off, and we light it off, and we'll go from there. Dean, he likes to use the word explode. He's like, turbine igniter explodes. I already showed you that at the beginning. Not a toy, I'm supposed to say. It will kill you. So don't play with it if you're not being super careful what's on the other end of the turbine igniter. They are very strong. All right, 100-hour gray box, and then we're out of here pretty much. Well, we're out of here at the left. So, here's our 100-hour box. In the top of it, there should even be a wrench for your spark plug. Isn't that handy? There's going to be a screwdriver for adjusting the points, specifically on specifically on Slick mags. Every box has one. That extra blue box in there has a bunch of extras. It's got the metal finger, which I'm going to show you in a minute. Hopefully they each have a screw for connecting the harness to the back of a Slick magneto. These are specific the way they're tapered, so you don't want to just put any old screw in the back of one of these. They're tapered specifically for it. So use the correct Slick screw when you're connecting them. The reason there's a couple extras in here, I have no idea, but they're in there. So we got extra. This we'll learn about. It's thread lubricant, anti-seize for our spark plugs. Spark plugs get super hot, and we want to make sure the spark plugs come in and out. These are adapters. On a Slick mag, the P-lead is right off the side of it here, and we'll learn more about how that's technically the capacitor as well. So easy connection if you just use a jumper wire onto a Slick P-lead. You're just going to connect it right to there. Simple enough, right? On a Bendix, on the other hand, not quite so simple. I actually don't have a full Bendix. On a Bendix, the P-lead is a threaded-on fitting, and you can't get a jumper in there on most of them. So each one of these boxes there's 2 different sizes where you can unthread the P-lead from the Bendix mag. You can thread these into the Bendix mag, and then your jumper wire or from your buzz box just goes on the end, and you have something to grab onto. So please, when you use them, put them back in the 100-hour box. And they should each have a Slick timing half moon thing. They each have the timing ring like I have on the front of here, which I'll show you in a minute. They should each have one of these. These are cool. They thread down into the spark plug. They help both for checking compression, which is Ryan's class, not mine, but it's in here. But the other thing they help with is finding top center on the compression stroke, remember. We always want to find top center on the compression stroke. If you're doing this on a very hot engine, sticking your thumb on the cylinder head will burn your thumb. So, or if you have short little arms like Ryan does, and you're working on a big 6-cylinder Continental engine, It's hard to be up front and put your thumb on the number one cylinder because it's afraid of the prop, right? It's all the way in the back. So that little bit of added length is actually just enough to be able to put your thumb on the top of here, which is not hot, and you can check compression stroke. So what this is for is as I'm coming through, if I had my thumb on here, right now nothing would be happening because my exhaust valve is open. So I've got nothing, and I still have nothing, nothing's going on. I'm on the intake stroke. Ooh, now I'm on the compression stroke, and it's building pressure, and it's gonna try to blow my thumb off the end of here. So I would use that to say, okay, compression stroke. Okay, so I found the compression stroke. So I know I'm on the compression stroke. So now what I'm gonna do is I'm gonna take this out. I gotta go to the next slide so you can follow along. Here's the short, easy version of timing. I found the compression stroke after I removed the spark plugs. Oh, I was supposed to spend more time on that. All cylinders, because as we're moving the prop around, we don't want to do just number one and be on the wrong cylinder and have it go bang and have the prop kill us. So all spark plugs, or at least all cylinders. Some people will get away with just the top cylinders. It's best to do all the plugs, but at the very minimum, all cylinders. So we located compression by our thumb here or using the yellow thing. Now I'm going to put this guy in. And you can make your own of these. Oh, I didn't bring mine in. If you take a spark plug and you, well, the high tension ones, or not high tension, excuse me, fine wire ones are easier to do it with. Come on, give me a normal. If you do a normal one, you can take a grinder, a cutter, cut the end off. You can weld a nut on the end and have a big ugly ball of weld on there and smooth it out, and it'll look basically like what I have here. Or you can just buy one of these aluminum things or use smats. But I made one, it's kind of cool, so then I have my own. Basically, you're just putting something in the cylinder. How far it goes in the cylinder, as long as the piston's gonna hit it, I don't care. The important part is that it doesn't change. So some people will be like, man, I gotta get that thing all the way down in. I'm like, well, not really, as long as we don't move it. But we'll say all the way down into there. So I'm on my compression stroke, we said, right? I backed it up a little. So what I'm gonna do, turn this so you can see it, is I'm gonna come until the piston hits. My piston just jammed on that. I can't go any further. And I go, okay, I'm gonna turn this to 0, or top center. A little tappity tap's always good, because sometimes they need a little bit of oil and they don't print. So I hit that and it says top center. Now I'm gonna go backwards, and it's gonna hit again. Ooh. All right, so I hit the first time, I hit the second time. This should be the exact opposite side. So halfway between those two hits, you would say is either bottom center, or when I go to the next, it'll be top center is what I'll show you. So I had adjusted it to top center. Now I'm gonna look at it and say, it says 80 right now. It says 80 degrees. There's a couple arguments on how I can adjust it from here. I like the easy way, that's foolproof. The instruction manual might have you go all the way right now. If it says 80, I could do some math and figure out where top center is going to be. But the easiest way to do this is to say, I'm going to go 80, take half of it towards top center. If you notice, I got bottom center and top center, only one direction's towards top center. So it says 80, I'm gonna go halfway, which is 40. Now, here's where the differences get. Some people would say, you already found it. Go ahead and take the finger out. When you get back to top center, you're top center. The problem is, if you messed it up, you won't know you messed it up. So the Case Visser way is, come back around and make sure you did your math correct. This should hit at 40 again. What's it say? Yes, 40. I did my math correct. So that's just a sanity check of I did my math correct. I take this out, and if I go to top center, I am now at top center. You notice the piston's as high as it's gonna get. This is a Continental. If I wanted to double check myself, I could go look at the flange and say, oh yeah, sure enough. This one is not labeled well, but the TC line is lined up with the bottom crack on the engine. Okay? Now, just for the fun of it, I would probably go backwards a little bit, put my thumb on it, and make sure one more time I'm on the compression stroke. Just to say I'm not 180 degrees off on this. Alright, so I'm going to do that one more time without any explanation in between, just to make sure. Make sure you guys are following me. So, I have no idea where I'm at. I'm going to put my thumb on here and rotate forward until I get where it tries to push my finger off. Not yet. Not yet. Okay, that's my compression stroke. So on my compression stroke, or not across it, it's half cut. I put my finger in. I'm going to come forward till I hit it. Put it to top center. I'm going to go backwards till I hit it. I don't want to break the piston, so don't go too fast. I'm going to take half the difference. So I'm at 78 this time, so I'm going to go to 39. Now, the book says I could take this out, but Case wants to make sure it says 39 this way. Hey, sure enough, 39. So that means I'm headed towards top center, and I could even check. Oh, good, compression stroke yet. Top center, compression stroke. Theoretically, this is where I say I put my mag on, but what we learned is that tag is going to say we want to be before top center, right? So we're going to come backwards before top center, and I'm not going to cover it today, but basically we're actually going to go past whatever number they tell us if it's 22 degrees, and I'm going to creep up on my 22 degrees to make sure that all the metal's pushing on each other the right way. I'm going to mount my mag, we're going to hook our wires up to it, and then we're going to come before this, and we're going to approach where that mag should open, and we should see the light go from off to on, right at the spot that it's supposed to say we spark. So that's how this kit works. We're going to go over it several more times in more detail, but that's the process of it, and I want you to see it multiple times as we go. Okay, we're going to run out real quick. I'm going to do this. It's 9:45. Yeah, that's right. So we got an hour left of class. Okay, tell you what, take a 8-minute break. At 5 to 10, meet me at, I got a mock-up kind of in the middle. We're going to do this on an actual mock-up as well. So we'll do that in 9 minutes out there. Meet us out there in 9 minutes. If anybody wants to see it here while you're on your break, that's cool too. You want to see it? All right, let's adjust it so we have no idea where we're at, right? So, you know what, I'll get it back up just so you can follow the steps. There's the basic steps, which you should pretty much be able to memorize. So, assuming we can't see what's going on here, I'll be your pressure man, because I will look at those. So, first step, we pull all the plugs out of all the cylinders. What's kind of wrong on this is, technically, that's not cylinder one, is it? It's not furthest away on my Continental. It should be over here. You know, it's the only cylinder I got to work with. So, we need to find compression first. So, are you going to be a long-armed guy or a short-armed guy?
I'll be a short.
Okay, so we'll put this guy in here. You're going to put your thumb on top of there, and then you're going to rotate the prop the way it should go. Oh man, that was easy. You already found the compression stroke. All right, cool. So you're on the compression stroke. Now you might want to go back just a fuzz, and the only reason I say that is just in case you were like at the top. All right, so swap those out. They actually make a tool that reaches through there, and it's a gauge. We'll learn about it in radio class. So they'll actually find top center by a finger indicator of the gauge as the piston comes up. So this is the old way. Okay, so So now we're gonna slowly go forward. Oop, so that's it. So hold it forward against it. And what number, well, not what number, we set it to 0. All right, so now you're gonna go backwards till it hits again. And when we get there, we'll split the difference.
Why? Like, what's the point of this thing?
So we hit, it won't allow us to go all the way to top center. So what I did the first time is I hit before top dead center. I'm going backwards now. I'm hitting technically after top dead center. So the first time I hit was before, the second time I hit after. So you're actually technically setting this to how many degrees after top dead center right now. So I'll point that out in a minute. So what was the first number we saw?
I think this is still.
Oh, 0 was the first time we hit, sorry. 0 was the first time we hit. So we're seeing 76. So what's half of 76? 38. So you're gonna wanna go to 38 towards the top center. Well, you go too far. Yep. All right, so to answer your question, technically, when we're gonna be going this way now, we are after top center, however many degrees. Now we're at bottom center. Now we're approaching top center again. And the sanity check is 37 before 38 before top center. So that's the sanity check is, okay, good, I hit it. So the way we got 38 is technically on this side, when we come back and split the difference, we're actually setting it correctly. So our rotation though is, we're setting it, it hit however many degrees after top center. We're just finding that in the backwards direction.
So when you divide in half, you're just making sure?
Yeah, that's how many degrees of travel we're not letting the piston go up.
So you're that many degrees away from
Correct, yep, we're that many degrees away from top dead center. So whether we go forwards or backwards, we're that many degrees away. Okay, so sandy check, yep, it's the same. So that's where we would pull that out.
And we have to do this because you have this thing that hits it, you don't know
if you
exactly
have
how
it at
far.
TC,
It's because we don't trust
should be
this
at
basically.
max, right?
Yep, so if you go to TC, it should be max. At this point, you could even be, yep, I'm still compression stroke.
So right there.
Right there, the piston should be all the way up. And if, does anybody have a flashlight on? The next sandy check is, this is a Continental. So if you look on the bottom of here, where is it? It's hard to see.
We can draw a line, but the Continental's bottom, like stuff.
Correct. So if there's a Lycoming engine, it would have a line right here on the top.
So then you would set your.
But this
your back
technically
there.
shouldn't make sense because it should be the first cylinder, right?
Which is probably why it's not at the bottom, it's hanging on the
Okay.
side.
Yeah.
That's why it doesn't make sense. Yeah, okay.
Yeah.
I was like, why is that not? Does it make sense right now? It looks like somebody dremel tooled it in.
Really put it in.
Alright, so it's, let me spin it around. I think what we're gonna find is it's not factory stamped. Well, top center's way over here. So if I keep my finger on there.
So they must have modified it somehow.
They must have done something, yeah. This is not a normal, normally on the Continental ones, it's on the edge, but.
Look at where our journal's at, it's pretty close to where.
Oh, you know what? These are opposite each other,
Yeah.
so something's a little bit,
So it's upside down.
here's the thing. Could this be a Lycoming engine upside down? No, is that number one?
And it's right ways up.
Back to, on an actual engine, that you can double check it with this. Some people will actually say, I'm not messing with this for climbing, I'm just gonna leave it here. And if you had it on here, what we would do is you would, oops, sorry about that. You would get to where I'm on my power, or my compression stroke, excuse me. So as long as I'm on my compression stroke, I'm gonna line them up. And that's what we're gonna walk out there and we'll do on, we call it a real engine where everything's assembled.
So then when you hit top dead center, is that where you put your mag in, or when you back
Well,
out?
So we're always gonna put it in before top dead center, and we will, let's label it.
So then you're still gonna use this to
So
set it
you're
a couple
gonna use
degrees
that
back.
to go back, so you'll use this to set it, yeah. And on this one, if I bring it around, and the Continentals will show similar, they'll show you both top center, but they'll also, before top center, they'll have a range of like 26 to 32. And
Where are you
So
mounted?
that's the range, like that,
That's gonna be the range of where a mag would typically go in. And we'll have that on slideshows later to say, I think they're often 2-degree increments per dash. You can confuse yourself pretty easy, but, yep. All right, I'm gonna go walk out towards that one. Basically, all that's gonna do is change the degree, right?
And you center this,
Yep.
top center,
comes back,
Yep. Yep,
that feedback over takes there, right?
we don't really care.
Okay.
I think,
85.
I think you're still on the compression until you get really close to the top. You're just coming back on that.
Right.
Well, you'd go compression to, yeah, intake, you're correct.
So,
So you're splitting the difference.
85 divided by 2 is 40. 42 and a half. 2 and a half.
Some of the air goes into the.
Right, and then I would come back,
So the manual says you're done. I like a good sanity check.
right there twice, cut once,
Yup.
And I'm looking at 50. Oh, no, that was 42. 42 and a half.
Yep. And then the last sanity check is you pull it out and you go, hey, am I still in compression stroke? Make sure I didn't somehow in the middle of that get myself crazy.
I'm not understanding how that, this trick does, how it gives you, tells you top dead center.
That might not be a review.
All right, we're gonna go out there. I would say
Yeah, it's
play
fine,
around with
it's
this.
fine, yeah.
take your time.
Once you do it once, I think you'll.
Like, I know the process, I'm not sure why
Goes around.
just putting that thing in, doing this way, going back,
Well-
tells us what we need.
Yeah, so.
Cause like, why would you,
What I wanna know is when it's all the way at the top, but what I'm doing is I'm stopping it before it gets to the top, so I'm stopping it here, right? And if I stop it there and say, okay, well, if I'm coming around this way, if I stop it at the same point, top dead center is gonna be basically halfway between
But some of it goes
those two stops.
through the crop.
So also you wanna make sure
okay,
the spark happens at top dead center, right?
Well, it's a reference point, it's before top, but yeah. So basically, what I did is I set myself up, I put a marker
Straight out.
essentially here with that, so that top will be there, and here's the other place I stopped.
Some of it
So
goes in.
it's halfway between those two is where it stops.
okay, I think that covers.
He's got back in here, right?
Yeah, just carry him with you. All right, we're gonna go do this on a real engine real quick.
I know, I thought about like,
How's it efficient?
Getting thrown around.
Still get messed up like, when they keep, do like, question for conversion. Oh, and ask for pressure and as well.
Not that.
No, I would love to see.
Dude, imagine if that shark gets your pet.
Shark's got fresh kicks.
Dude, even the back fin has a shoe on.
Wait a minute. What is that on?
Oh, yeah, it's
Tail.
got a bit there, doesn't it?
Yeah,
He's
he's on
another
there.
board. The tail eater shark.
I mean, I would dress your shirt. I would think that would be
have
right
right
on
on
the toes on that one.
And
What's your password?
thoroughly confused.
Dude, Matter made he did it again.
Hold on.
What'd you do?
Change matter. Wish nobody's
How do you do that?
Change matter baby language.
Yeah.
Change it to Arabic.
This?
I don't know, but I'm gonna quote Penny. That shark's got fresh kicks. Unquote. Unquote.
Oh, we only have like 35 minutes till lunch. We probably shouldn't do this last part there.
Yeah, that would be irresponsible. It's gonna be displayed.
Darn it. Wish I had more time.
Anyways, I'm gonna go get some nuts.
Anybody else ready for the weekend?
What?
I'll be working on the weekend like
What
that.
have you been working on?
David. David. What do you do tomorrow? Why is there a shark with shoes?
What is that? Bro, why are out my wheels?
You would love this video. It's an Australian guy talking about the deck he just built. Alright, open lab one. I love Australians. It'll make a lot more sense if you wait till after the lecture shoots it.
They just have to build everything.
Challenge accepted.
What are you telling me about?
Sometimes looking at it, you don't do anything else though.
Correct, and that's why, which is, it's
So
the
that's the
second
average.
closest way to go.
If there's two or three that are like, okay, I know for sure.
How much
Probably
time?
why it's so
Yes,
wide.
that's what I'm saying.